Okay, welcome to the next part. Here we have to discuss the theories of coordination compound, and we already know discussed about the coordination terminologies and nomenclature, right? Okay, so there are mainly four different types of theories of coordination compound. The first one, that's a simple one, a Werner theory of coordination compound. The second one, that's actually Sidgwick theory of coordination compound. Third one, valence bond theory. And the fourth one is crystal field theory. Okay, so these are the important theories of coordination compound. Okay, so let me discuss about the first theory, Werner theory. Okay, Werner theory of coordination compound. Ready? Fine. And there are some postulates for your Werner theory. Okay, let me discuss that. Ready? So the first postulate, that is let me discuss the postulates. Okay, first postulate, that is actually in a coordination compound there is a central metal, right? Okay, and this is the first theory which is introduced in case of coordination compound, Werner theory. Okay, so in a coordination compound the central metal have two different types of valencies. In a coordination compound, your central metal possesses two different types of valencies. The first one is primary valency and the second one is secondary valency. That is the first postulate. Okay, so in a coordination compound, central metal have two different valency. Your central metal have two different types of valency. Okay, the first valency, that is primary valency, and the next is secondary valency. Okay, actually the primary valence is our oxidation state and the secondary valence is the coordination number of central atom. Okay, nowadays we know what is oxidation state and coordination number. So that's exactly the primary valency and secondary valency. Okay, so fine. The primary valency is the residual charge on central metal, let it be Cm. Okay, and we know that primary valency, residual charge means that's equal to the oxidation state of central metal. Ready? Then what about the secondary valency? Secondary valency is actually the number of coordinate bond around central atom. It is the number of coordinate bonds around central atom. Number of coordinate bonds around central metal. And we know that the total number of coordinate bond around central metal is said to be the coordination number. Ready? So in today's terminology, that secondary valency will be equal to coordination number of central metal, coordination number Cn of central metal. Okay, fine. Listen, what about the next point? The next point is your primary valency usually ionizable. Okay, we know that the primary valency, which means the positive charge of metal, it may be satisfied by either the negative ligands or by the negative counterion. Okay, so that primary valency may be satisfied by ligands or counterion, right? Or any kind of positive ion, positive or negative ion. So usually ionizable and represented by represented by dotted lines, represented by dotted lines. And what about here? Here the point is non-ionizable, always non-ionizable. It may or may not be ionizable, but here always non-ionizable. Your secondary valence is always non-ionizable. Okay, and it is represented by dark lines. Your secondary valences are usually drawn like a dark pattern, but this is something like a dotted line. Okay, ready? Fine. Number 3, the third concept. The third concept, that is, listen. Fine. The next, present outside of sphere. Right. We know that the counter ions are outside of sphere and satisfied by positive or negative ions. The charge, the oxidation state of metal may be satisfied by positive or negative ions. Okay, and this is, we know that the ligands indicates the secondary valency. Always the ligands are present inside the coordination sphere. Okay, so present inside sphere and satisfied by, we know that the ligand satisfied by ions or molecule. Ions or molecules. Okay, fine. And the next postulate, that is number 3. We all know that groups attached by secondary valency, which means the ligands have a definite geometrical pattern around central atom, and that is referred as geometry. Okay, so that is the next point. Groups around central metal by secondary valency, which means your ligands have definite spatial arrangement. And they all have a definite spatial arrangement. Okay, ready? The next, that's all about the Werner theory. Listen, if I have a molecule CO, H2O, 4 times Cl2, Br. Okay, fine. What about the case? Secondary valency. That's a coordination number. Coordination number means the first ligand aqua with a density 1 into 4, plus second ligand chlorido, density 1, number 2. So the secondary valency is 6. What about the primary valency? This is -1, this entity is +1, this will be a -2, so this is 0, so this one will be +3. So we know how to find the primary valency and secondary valency of metal. Okay, we already discussed it is in an alternate terminology like oxidation state and coordination number. So we know that. Okay, fine. So here the primary valency is 3. Ready? Here the molecules of primary valency. Actually, the 3 primary valencies are satisfied by 2Cl minus and 1 Br minus, right? 2Cl minus and 1 Br minus, agreed. And the secondary valencies are satisfied here by 4H2O and 2Cl minus. And it is perfect that these all are ligands which is inside the sphere, non-ionizable. So your groups of secondary valencies are always non-ionizable since they are existing inside of sphere. Whereas groups of primary valency, here Br minus is ionizable. This is ionizable. Okay, but this is not ionizable. So these 2Cl minus, which means ionic ligand which can satisfy both primary valency and secondary valency simultaneously. Ionic ligands can satisfy both primary and secondary valency simultaneously, but it is non-ionizable. Okay, fine. So usually groups with the primary valencies are ionizable. Usually, sometimes it may be non-ionizable. For example, I have another compound CO H2O 6 times all of Br3. Okay, here the groups of primary valency is 3 Br minus, right? The primary valency is plus 3. And that plus 3 or the 3 primary valency which is satisfied by the Br minus, okay, actually 3 Br minus, where these 3 all Br minus are ionizable. So usually groups of primary valencies are normally it is counterion in sometimes it may be charged ligand. So if it is a charged ligand, it will be non-ionizable. If it is a counterion, it is ionizable. We know the concept. Okay, fine. So that's all about the Werner theory. And one more thing. Werner put forward these postulates on the basis of study in chlorocobaltamines. Okay, so study of chlorocobaltamines. Okay, fine. Chlorocobaltamine means CO NH3 6 times. I'm sorry. CO 6NH3 CO Cl3 6NH3. This is a case. Okay, and using this molecule, he did a lot of experiment, and he found that when this on treatment with the excess of AgNO3, the precipitate over the number of moles of precipitate are different, right? We already know that if we have XCl minus, and when it is reacted with the excess of AgNO3, we forms X mole AgCl, white precipitate. Okay, and on the study of chlorocobaltamines, he found that a molecule which is of 1:3 electrolyte, which is of the type 1:3 electrolyte, okay, and which can produce 3 mole AgCl when react with the AgNO3 from that chlorocobaltamine, and he formulated that molecule as like this: CO NH3 6 times Cl3. Okay, this is a case of 1:3 electrolyte, because when this on ionization, what happened? It becomes CONH3 6 times of 3 plus 3 Cl minus. Okay, so this is of the stoichiometry 1:3. Okay, so he found that a 1:3 electrolyte can be formed from the chlorocobaltamines, and which can form a 3 mole AgCl precipitate when react with the AgNO3 ready. And he realized that what the formula will be like this. And he found that the color is yellow colored one. The compound is a yellow colored one. And later in his study, he found that there is a 1:2 electrolyte, 1:2 type of electrolyte, and which can produce 2 mole of AgCl when it on react with the when it is on reaction with the what? 2 mole AgCl when it is on reaction with the our AgNO3. And he formulated that the formula will be CONH3 5 times Cl of Cl2. Okay, then only it may satisfy like this: CONH3 5 times Cl all of 2 plus 2 Cl minus. So this belongs to a 1:2 type. Okay, and this one have a color of purple. You observed that that typical chlorocobaltamine, which can produce 2 mole AgCl, have a color of purple. But the one which can produce 3 mole AgCl with the 1:3 type of electrolyte have a color of yellow. Okay, so he realized that using the very same formula, using the very same entity, cobalt, chlorine, and amine, we can produce different types of compounds, and that is the initiation of the spark which leads to the development of coordination compound. Okay, fine. And he found that there is a 1:1 type of electrolyte, but that 1:1 type of electrolyte which actually exists in two different colors. That means it can exist in green as well as in violet color. Okay, and that on a reaction with the AgNO3 forms 1 mole AgCl only, 1 mole AgCl. So that is entirely different compound from the previously discussed one, okay, or the before one. And he found the formula, or he formulated that it may be something like this. Okay, because this on ionization forms what? CO, NH3, 4 times Cl2 all of plus Cl minus. So this is a type of 1:1. Okay, so the very same form can have two different color, green and violet, and he realized that the molecule with the same formula like that but different properties. Okay, so that may be any kind of isomer. Okay, fine. So he realized that there may be a chance for the isomers in this kind of molecular compounds. Okay, that is exactly the first initiation which leads to the development of what? Coordination compound. Ready? Fine. So let me write 2 questions. Find primary and secondary valency of following. Find primary and secondary valency of following. Okay, it is nothing but your coordination number and your coordination number and oxidation state. So this is the first molecule. Okay, fine. Here the ligand is oxalato, right? So first you find the secondary valency. Ligand is oxalato, density 2, number of ligand 3, so secondary valency is 6. What is the charge of central metal? That is oxidation state. So what about the primary valency? This is of +3, so this will be -3, and -2 into 3, so this can offer -6. So the chromium will be +3. So the primary valency is 3. Okay, here this is a molecule tris triphenyl phosphine let it be 6 times. Okay, I'll leave it. No need of 6 times, 3 times. Tris triphenyl phosphine, nickel 2. This is 0, nickel 2. Ready? Fine. For the primary and secondary valencies. Primary valencies 1 into primary valency, the oxidation state. Oxidation state of nickel is +2. So that will be two. Secondary valency, the coordination number, density 1, number of ligand 3. So that's 3. Okay, fine. Ready. And one more thing. So let's consider the molecular arrangement of or the diagrammatic arrangement of Werner concept. So this is cobalt with coordination number 6. So having formula like this. Ready? And here is the 6NH3. Clear? And there is 3 Cl also. Cl like this. Cl3 which satisfies the primary valency, right? So if it satisfies the primary valency means they are represented by dotted lines. And NH3 satisfies the secondary valency, so they by dark lines. We already discussed that idea. Okay, fine. The next is CO. NH3 5 times Cl, all of Cl2. Okay, so once again the secondary valence is 6. So having a geometrical pattern of octahedral. So find which satisfied by 5 NH3. 5 NH3. Listen carefully, and the one is a chlorido ligand. Now draw the primary valency. Primary valency is satisfied by 2 counterion Cl and minus 2 minus 1 plus 3. So this plus 3 satisfied by a ligand Cl minus and 2 counterion Cl minus. So the counterion primary valency Cl minus represented or all with the primary valencies are represented by dotted lines. So this is a dotted line. And this is something which can satisfy both secondary and primary. So they are represented using dark as well as dotted line. Both dark and dot are represented. Okay. And the next is CO. NH3 4 times of Cl2. Okay. Outside of Cl. So once again the secondary linkage, secondary valence is 4. So like this. Here is a Cl, here is a Cl, okay? And one pure primary valency, one pure counterion is there, which is represented by dot. And these all are can satisfy both primary as well as secondary, okay? Fine. So that's all about the Werner theory. Ready?